Hello everyone, I am Kosuru Ganesh Venkata Nadh. I am an tech student from Department of Electronic Systems Engineering in the branch Electronic Product Design, and I am a CNS scholar for the year 2023 to 24, and I am currently doing a project under CNI and DESC named IoT-Enabled Universal Authentication Platform. So we know that Aadhaar is the current largest biometric system in the world with almost 133 crore active users. So the thing is that the current registration for Aadhaar is under controlled conditions. That is, you should have controlled lightning conditions, and you have to place a proper capturing poses, and the aging factors are very much high where we cannot authenticate some elderly people and different sensor variations. And so our motivation is to authenticate a person and even under harsh conditions like this to avoid spoofing attacks, etc. So our equipment will have signatures from two modalities. One is fingerprint, and during our literature survey, we found that we can also authenticate a person based on the shape of the ear canal. So through literature survey, we got the idea, and now in this product, we are trying to integrate two modalities. One is fingerprint, and another is ear canal. So this is the functional block of our product, where there are two modality signatures. The first signature is through fingerprint, and the next signature is through ear of the subject. So we will capture the fingerprint through a capacitive sensor, where the current Aadhaar currently uses optical sensors. The capacitive sensors are very different from optical sensors because optical sensors try to capture the image of the fingerprint through light, where capacitive sensors convert the uh, fingerprint to a encrypted form via taking the voltage levels difference between the resistant values of the fingerprint. So another modality is ear canal of the subject, where we place a speaker and we emit some audible range of frequencies through microphone, and we capture some reflections from the ear canal through a microphone which is placed very in proximity to the ear. So we want to study that reflections based on the ear canal shape, how the shape of the ear canal is, how much curvy it is, how much uh, bony it has, and different acoustic features of the ear canal. So we'll take the signals from fingerprint and ear canal and send it to a microcontroller, and then we run various scripts to bring out the data and to study the feature. So our product has different functional blocks. One is main processing module, which is NRF52840. It has Nina BLE module and ARM Cortex M4 processor. And our sensors are 9x IMU, microphone, and fingerprint sensor. Through microphone, we capture the reflection from the ear, and through fingerprint sensor, we capture the fingerprint of the subject. So the communication of fingerprint is through ER to microcontroller, and the microphone converts the analog signal taken into punch density modulated wave. This PDM wave is given to the microcontroller for processing. And then 9x MMU is to adjust the speaker to the right position for the subject. And this communicates to the microcontroller through I2C communication. So this is a schematic circuit of the main PCB board, where we have Nina BLE module which has ARM Cortex M4 microcontroller, and we have different USG protection circuits, reset circuit, power selectors, LDOs, repo chargers to charge the battery, and different interfaces to connect the sensors, etc. So the right side figure is the 3D view of our PCB, and left side is the schematic of sensors. So the algorithm which you are following currently after extracting the reflection signal from the ear is, before extraction, before generating the signal, what we are doing is we are creating a linear chip signal which has increasing frequency from 0 to 20 kilohertz, which is in the audible range of the human. So that signal is sent into the ear, and then reading the reflected signals in the form of dot wave, that is audio file, and then performing FFT to convert into a frequency domain analysis. Visualizing the FFT plots, where we got the idea that there is something unique in this, and then extracting null frequency substitute coefficients, performing principal common component analysis for dimensional reduction, and finally extracting the feature and matching. So these are two FFT plots, ear canal resonance spectrums, which are shown, where it shows that these are taken for two different subjects. So these two specters are very different. So the position of peaks of spectra determine the length of the ear canal, and the height and width of the peaks determine the ear canal shape and maybe skin's hardness. So they are giving some acoustic information of the ear canal. So another comparison was, as our 10 fingers have different fingerprints on our hands, similarly our 2 ears ear canal shapes are different, as we can see in these plots. So the features of left and right ear canal shape of the same subject are different and unique to the corresponding ear of the subject. So when we compare the position of the microphone results when changing the position of the microphone, we can see then also we are getting some changes in the reflected spectrums. So we can see that the position and height and width of resonance vary depending upon the position of the microphone. So to control the position of the microphone, you are using 9x and IMU, which is very close to the microphone. So IMU sensor is used to determine the microphone position and thereby take the readings. So these are null frequency substitute coefficients which are accepted for different wave time frames. So the table left shows the MFC of subject 1 and table 2 shows the MFC of subject 2. So initially we said that we are going to authenticate a person in harsh condition. So that initially we did some experiments using optical fingerprint, where currently Aadhaar is using. There we unable to capture some fingerprints which are dusty and also which are some oil and wet. You can see that the two authentications had failed due to this improper conversion from template to hexadata. So this data is not matching even for the same finger when then captured in different conditions. So this is the drawback of the optical fingerprint sensor. So we used thereby a capacitive fingerprint sensor, where we can successfully authenticate a person even if his hands are dirty, wet, oily, greasy, etc. So these are the different images taken while the person is successfully authenticated in harsh conditions, as I have mentioned previously. So this is our total hardware, where it has a fingerprint capacitive scanner and the board, PCB board, and one speaker to emit the microphone, and you'll have a IMS sensor very close to it. And this is a hardware, and this is how we are taking the readings from a subject, how we are trying to authenticate a person uh, by sending the signals into the ear, and also by collecting the fingerprints and authenticating. And this is the GUI which we use for connecting with the device and to operate the entire operation of the board. So the challenges in the current fingerprint are eliminated by using capacitive sensor, and also spoofing attacks are somewhat can be reduced by using this acoustic ear canal based modality. And there is one limitation which we overcome by using a microphone very proximity to IMU sensor, where IMU sensor detects the position of the speaker and the microphone. So we can use other modalities in integration with this, such as iris, face, voice, which can be included to increase security. And also we can further make this system entirely wireless, so that it acts as a standalone device uh, with already battery attached to it. So this is our work, and I'm very thankful for CNI for supporting us in doing our projects. constantly giving us inputs and making us move forward in completion of the work. Thank you, CNI. Thank you, everyone.